So a news article I didn't get to that I'm going to mention is that the coders are really very good, and they really are. I can just go to Google and say, write a Python script to do something, and blam, I get a Python script. All the coders have noticed the AI coding is getting very good. And they say the old stuff that coders used to do, they're going to call that syntax coding, where you type all the code and you put in the right semicolons and everything. They say that's pretty much extinct. Now you let AI do that for you. You describe it, and it fills in the syntax, which, but it still makes mistakes. You're more of a manager overseeing the AI. And I think that's one area where it really does shine. And getting all the little semicolons and stuff right is the kind of job appropriate for a machine more than a human. So you have to understand it's an assistant to do the boring, repetitive stuff for you, but you have to add all the intelligence and judgment and yeah.
Does that mean that you still rely on the machine, or you can rely on the machine to do things like make distinctions between what should be coded as a string versus an integer versus make those kinds of decisions.
Yeah, it chooses. Yeah, it chooses.
For higher level decisions, I guess the developers like, what classes make sense. How does the actual sequence of the program as it's run make sense? Is that sort of where you're thinking that we fit into the workflow?
Yes, and what I hear when I read these articles and developers saying, if you're just trying to make a prototype, and you're a beginner coder, it's great for that. But the next thing is kind of forces you to go to the next level of professionalism, where you not only write code, but you write tests that make sure it's working. And that's what you'd have to do, because the AI is very likely to make mistakes. And you really should be writing unit tests for your code. And then, but they say at the next level of professionalism, real enterprise code, a lot of them are abandoning it because they say this code is sort of sloppily and inconsistently written, which means we're building up technical debt for the future when we try to make later versions and revisions. However, I think that's temporary, because I think you could add to your AI prompt our company manual, our style manual, and get it to write code obeying our rules for the comments and everything. I don't think that's happening much yet, but I think that's the future. And that's why they say the hiring of junior coders is probably going to have to change. There will be no junior coders. Everybody's going to have to be up to like an intermediate level where you're the manager effectively.
And so, sorry to keep asking questions.
Yeah.
That comment structure that you're talking about will then make the code for future generations, as you're alluding to, understand more depth of what the original pieces do, so as they build on and add on, it's more standardized, cleaner, more efficient, runs better, et cetera, et cetera, et cetera.
Well, that's the hope. But in practice, that's why when I first heard about cars driving themselves, I said, well, that'll be great, because I rode a bicycle everywhere, and I said, I know how terrible people are. Yeah. I said, it'll of course be better than the people, and it turned out that's not true. Teslas are actually more dangerous than people, so I assumed it would be designed well, but that's not true. It's true of these Waymos, but they cost more than 10 times as much as the Teslas. The Teslas have crimped the cost too far. So you would like to think that it would beautifully be consistent, but unfortunately, I know from early tests, it will do things like write comments that say, here's how it works, and then the code is not really doing that. Like when I asked it to solve problems, it would give me a page out of a manual that says, okay, here's the code to solve your problem, and here's the answer, and it would do the right answer, but when you run that code, you don't get that answer. Because you have to understand what it's doing. It's making it look like a page or a manual without understanding anything it's doing.
Yeah, so this brings me to a question that I didn't get to ask last week.
Yeah.
So the riddle exercise that was in the week one module, where you take that classic riddle of the farmer crossing the river.
Right.
So I did that exercise with ChatGPT and Gemini, and it spit out, ChatGPT just was happy to spit out the old answer.
Yeah.
Gemini made the distinction.
I know what.
It said, well, the way you've entered this, the old answer would have been this.
Yes.
But since you say the compartments are on the boat, the new answer is this.
Yeah, which is a better answer. However, if you just rephrase the question and ask it 10 times, you'll find it doesn't always get it right.
Right.
And so there are benchmarks where they try to rate the quality of these AIs, and they are improving. But so far, most of the ways they improve them involve consuming much more CPU power for each level. Like these thinking models really spin for a long time, and that's why they're building more and more data centers and buying up all the GPUs in the world. And I'm now seeing articles where people are saying, it looks like these proposed data centers are never going to be built, because people are beginning to say, where is the profit to pay for all this? And, about 3 weeks ago, the chief financial officer of OpenAI said, well, we're going to need the government to backstop these loans.
Yeah, you talked about this last week.
And then, but 2 days ago, the head of Gemini, Google's CEO said this, Microsoft CEO said the same thing. I'm getting pretty nervous about this. I'm afraid unless we can start having AI produce a product that is used by non-tech companies, we're never going to get this money back. But they're all beginning to admit, we spent trillions of dollars on this stuff and there's no product that can remotely make that back. Yeah.
So one more question, sorry.
That's fine.
So what about companies like Amazon and Google, which both have huge data center infrastructure that's existing already? Specifically, you're saying because that data center infrastructure isn't GPU,
right?
They're going to have to build additional data center structure on top of what they already own.
Yes, that's the incredible thing. The gigantic, monumental data structure of Amazon is not remotely powerful enough to do what they're trying to do now. And that's why the problem is these AIs, people, all the assumptions that it's going to make a lot of money, assume it's going to get a lot better than now. Because what they have now is like the beta version, but they've already pretty much hit the limit of the power grid and the data centers. So if everyone is willing blithely to invest another $10 trillion in the data centers and cause all the pollution from all the power plants and everything and not complain about that, maybe they could get significantly better, but it's not likely to happen. And that's why I really think Gartner has it right. It's at the peak, and it's starting to fall down when people begin to realize, hey, this isn't that great, and it costs too much, and there are problems. So
it's just crazy to me, because I got my AWS certificate last semester, and learning about the scope of their network and their infrastructure is just kind of mind-boggling as it is.
It is.
But then to hear you say that is
these things
it's
demand.
hard for me to conceptualize.
I know these things demand a ridiculous amount of compute for the results we're getting, and we're not remotely paying for it. Everything we see is a loss leader. They're all providing a product that's very expensive. Like I remember they said an average Google search costs like a few pennies, but an AI Google search costs like 10 or 20 bucks each or something a while ago.
Will it lead back to the old way of doing business where every company has their own data centers?
Well, that would only work if they get enough profit to pay for it. And so these small local models you can run locally might be the way of the future. That's what I always thought. I mean, the fundamental problem with the large language models is they solve every problem. They have the whole internet. Training a model to just do one thing, like, for example, write Python code, where all it does is train on a few Python manuals, that would probably be a small thing that wouldn't use all this power. So I always thought that's where we're headed. Small, local, specialized models that don't require a huge data center.
The same idea is kind of right-sizing a query, right? Where you make an index of a copy of a database rather than querying the entire database because you just use up so much time and compute power to make that happen.
Yeah, and another thing that's happening, by the way, is that, they have these context limit, how much you can put in the query, like 80,000 or 100,000 tokens, which are basically words. It turns out when you do something tasks like coding and it does the thinking, it keeps adding more and more to that context, where every new question has all the previous versions and all the criticisms, and pretty soon you hit the limit, and then it starts compressing the context to make it fit. And one of the things they're discussing on the AI chatbot forum is, I really hate it when I start forgetting things because I'm forced to compress the prompt to fit in the limit. So that's why it's so expensive. I mean, you ask it a question like,
"What?" Come out with something called a conductor, where it keeps the context as part of the code itself in Gemini 3.0.
Well, the context is part of the prompt, not necessarily part of the code itself, but all previous versions of the code are now part of the prompt. That's why it sort of grows and grows and grows exponentially.
Isn't there a product called a conductor in Gemini where they are saying the context becomes part of the code so that you don't have to remember the context every time?
Well, I don't know. You might put it in the code, but even if you do, then if you revise the code, you have to run all that through again. So, I mean, you could say these AIs are spectacularly inefficient. They keep having to process this huge block of data and then process it again and again. So there may be ways to make them more efficient in many ways, but the current generation of them are extremely wasteful and demanding. Anyway, this is all very good stuff. Anyway, let's talk about how we're modeling data. So here's the steps to making a machine learning project. You've got to get your data. You have to explore and visualize the data, choose your algorithms, train it, fine-tune it, and then the thing that a lot of people overlook, you have to launch it, you have to monitor it to see how well it works, record the errors, record the complaints, and test how good it is, and then maintain your system. So you get real data. There's a whole lot of online repositories of real data out there to work with if you're going to. And so then you have to look at your big picture. So in this case, we're going to do a problem where we're going to try and predict the housing price of houses in California from some data which I imagine came from the government, which breaks California into a bunch of districts and gives you information about those districts, like the number of bedrooms in houses and so on. And then you're going to make investment decisions. How much should we invest in real estate is the idea here. So you have the data, and then you're going to predict prices, and then you're going to put them through some investment analysis based on that to decide where to make investments. And we're not going to do this. We're only going to do this part. Yeah.
So what's labeled here is upstream components is anybody who's collecting data, like a realtor or something, and feeding it into the state data.
Well, it could be. And of course, the issue is data quality and data reliability. In this case, we have one fixed data set we're going to use.
Right.
But yeah.
Which we are just saying we accept. But
right.
For the purposes of the future, this would be the point at which you would say, okay, some of this data is valid, some of it's not. We need a mechanism here before we put it into the distinct data bucket to know that it's good for the model.
Well, yeah, that's basically what we're focusing on here is how do you handle real world data, which has a lot of problems.
Okay.
And so you can do supervised learning if your data is labeled. You can do regression if it's going to predict a value. You're basically putting a line through some points. And you can do batch learning if you're going to train on this data and you don't plan on retraining on future data later, which is what we're going to do here. We're going to take one set of data and train on it, and that's as far as we want to go for what's happening today. So you could use multiple features to predict a value, and that's what we're going to do. You don't just have X and Y, you have like 10 measurements and use all of them together to try to predict the median house. You could predict a single value or predict multiple values. In our case, we're going to predict one value. We're trying to predict the median price of houses from other information about the region. So you have to have a performance measure. You have to have some kind of measure of quality of your results. And the most common one, been used for centuries really, is root mean square error. You take the difference between the predicted value and the real value, and you square it and add them up. And clearly you want to make that as small as possible. That's fitting as close as possible to the data. This is called the Euclidean norm. And in machine learning, we're going to call it L2 because it measures the second power of the error, that's square. This means that large errors are considered much worse than small errors. That's what the square does. And you may not want that depending on the type of data. The alternative measure that you will sometimes use is just the L1, where you just take the sum of the absolute value of the error so that large errors are not heavily weighted compared to small errors. And it just depends on the kind of noise in your data, which one of these is appropriate. So the price is going to be a numerical value. Now, if the next stage uses categories like cheap, medium, or expensive, then you use classification instead of regression because you don't predict a number, instead you predict a category. And we'll get to those later, where you just sort things into categories. Machine learning can do that too, but it's a slightly different algorithm. So you get the data, and so we can load the data from GitHub, and we'll see it down here. And if you just do the head, you'll see the first 5 rows. So let me just do this live. This is a project you'll be doing based on this chapter. And so here, I'm just going to get started with this thing. This is going to download the package versions we need. We're using sklearn, one of the main machine learning projects. And this is the thing that just downloads this data from a public source of data to practice on with AIs, like I said, a bunch of them. And this is housing data, some data set, which I imagine came from the government, although I'm not really sure. But somebody made this data. And then you can use head to get a look at what the first few rows look like. And see, I think I didn't run this one yet. There we are. So here you get a summary of the columns: longitude, latitude, the age of houses, total rooms and total bedrooms, populations, number of households, median income, median house value, and ocean proximity. So this is labeled data because we're going to try and predict this number, and we know the right answer. So we're going to try to use all the other numbers to predict that number and measure how close we get to it. That's what our model is going to do. Yeah.
I just want to ask a couple questions. So
yeah.
We obviously have the column headers by the names. Then when you have the non-null count, that means that you have no data that is equal to a 0 value.
Right. And you see some of these are null.
Right.
in the total bedrooms, and that's one of the many problems with data. Some of them don't fill in all the fields.
So you have someone who's entered a house, but they haven't bothered to enter the value
Right.
of whoever's tracking that data.
Right.
So you know you have some bad issues.
And I've seen, like when Radio Shack I used to go to, and every time you buy a product, they would ask you for your phone number and your address. And a lot of people didn't want to give it. So since they didn't make the database able to do that, people just put in dummy values, and that's another problem.
Right.
Often your data contains fake values.
Right, okay. And then for the data type, when you have float 64, that's to the 64th decimal point on
64 bits.
64
bit decimal numbers.
Got it.
And this one here is something different, ocean proximity. So if you look at the first 5 records, which is what you get from head, you see longitude and latitude makes sense, median age makes sense. It looks like it's rounded off to the nearest year. Its rooms is fine, total bedrooms, population, households, median income looks pretty good, and median house value looks good, but proximity is screwy. It's not a number, it's alphabetical. So that's going to be an issue we have to deal with. It's data, but it's not numerical data. All right, and so if you want to look at the proximity, you can do that with, let's go back to my, all right, so to get more information about that, this will give you the count of how many there are in each category for a data item. It looks like the rest are pretty self-explanatory, but this one seems to need a little more explanation. So now you see, here's your choices. And there's only 5 on an island, and the others are described by how close they are to water. So there are 5 categories, non-numerical. All right, so now we know what we've got in the way of data. You can use describe to see like mean, standard deviation, and minimum, maximum of them. And here, actually, this is important, and let me bring it up, because this is a problem we're going to hit a bunch of times. Now, we were going to take the mean squared error, but if you look at it here, okay, the data is all in different units, right? Longitude and latitude are in degrees around the Earth. The age is in years. The rooms are counts of rooms. The population is counts of people. So if you just take this data the way it is, then it is going to decide that longitude is far less important than rooms because rooms is bigger, just because it's on a different scale. This is going to hit us. That's why one thing you often do is scale everything to go from 0 to 1. Or consider, do you really think this is more important than that? If it is, then that should be at a different scale. But if you don't scale your data, then the relative importance of these things is going to be determined by the units in which it was measured, and that's not a good idea. So you make these histograms, which are one of the really important steps in trying to figure out what good your data is and how you're going to use it. So here we'll have histograms coming. There we are. So this shows you total rooms, longitude, total rooms, you see the distribution of it. Now, longitude and latitude are not remotely Gaussian curves, of course. There's 2 zones. There's near San Francisco and near LA. And pretty much everything is in one of those 2 places. So these are bivariate things. And the housing median age is really screwy. There's a peak at one time and a peak at another. That probably reflects like a bunch of houses getting built with the GI Bill after World War II. And another boom like in the 80s or 90s building houses. That's believable. This is not believable. This apparently indicates that they just put 50 in for anything bigger than 50. And therefore, 50 doesn't really mean 50. So in that 50 should be treated as like a category, not as a numerical value. And that's going to be an issue. Then you got, this is pretty much a Poisson curve, and those are Poisson curves, which is what you'd expect, like Gaussians, but sort of skewed toward 0. But here you have another one. The house value hitting a strange maximum that just seems to be the limit. So again, this is probably a categorical bit of information, not a real numerical bit of information. So you're going to see, it's nice to write like mathematical equations in the ideal case, but the real world is very far from the ideal case. So if you create a test set randomly, I think I won't bother doing it live. I guess I will because we're going to need it. All right. If you take the logical scientific thing you'd think to make a test set and now remember you want to take something like 80% of the data and train the model, and you want to take 20% of the data and test the model, showing it data it's never seen before. So how would you do it? Well, the simplest thing would be just to randomly pick out a training and test set. And so you'd have, here's the head of the test set. All right. So that shows you your training set of 16,000 and your test set of 4,000. So that doing it randomly would be okay, but there's a reason why you don't want to do it that way, and that's biased sampling, which I think I mentioned last time. If you have something that depends on sex, where men are different than women, then men and women are not 50-50. It's 51% women in the population. And so if you just take a group of 1,000 people and give them 51.1% chance of being female and take random samples, your sample might contain only 47% women or 54% women. So your sample might introduce a bias. This is not the best way to sample when you have a variable that has a big effect on the thing you care about. What's better is stratified sampling. You break the categories into groups and you choose random samples within each group. And here we've observed that income is between 1.5 and 6. It's in some scale, and there are some values up to 15. So then the income, as you would imagine, is a very strong predictor of the house value. The rich people pay more for houses than poor people. So instead of just randomly sampling by income, we're going to break it up into 5 bins and choose the right percentage of each of these bins. So we get a much more accurate sample. So that's what this is going to do. All right. And that's going to define my income categories and determine how many there are in each of the income categories. And then we're going to split the data according to those income categories. Taking the right number in each category for the test set. And so now the training set has like 35%, 31%, 17, and the test set has 35%, 31%, 17, and so on. It's much more representative of the real data. So again, what we've done here, I mean, if you think about like polls to predict who's going to win the election, that's what I was thinking about when I first learned this. You understand why it's such a mess, how you can run a poll, and then there could be another poll that has a contradictory answer, because it's not just counting the respondents, it's all these adjustments made by humans, and disturbingly likely to be wrong, where you chose one variable to matter and selected by it. The other person might have chosen a different variable to matter. And I know in election results, you often can't get enough poor people or enough black people to respond. So you somehow try to multiply those numbers by some value to compensate, but then you don't really know if you got it right. And you often assume that it's going to be the way it was in a previous election, where this percentage does this and that percentage does that, and that might not be true. So, you know, the machine learning cannot make up for the fundamental flaws in your data, but you do what you can. So here's what you get to choose 20% of the data. Here's the unstratified data set. I don't think I really need to make that. Anyway, so when we're done, we can remove the income category problem. I think it's okay that I skipped a couple steps there. We're going to find out. All right. And now, now we can visualize the data, which is the way you're going to see what other problems we have to cope with. So yeah, here you get a scatter plot of the geographical location of all the data, and this is a very deceptive plot because there's a lot more near San Francisco and LA than you see here. The dots are overlapping to where they're wiping each other out. So if you use transparent dots, it will be easier to see what's really happening here. Now it's more easy to see that there's a really dense region here, and these are really just a small number of people out there. But you can also add population and price in colors. So you get more of the many variables represented here. So now we've got median house values in the color. So you can see that all these rural houses are really cheap, and it's in the center of these dense zones that you get the really expensive houses, which makes a lot of sense, of course. And of course on the coast to get the ocean view. So you can do correlations, and these are going to begin to show us which variables are more important. So here you get the correlation coefficient tells you how predictive something is. House value is 100% predictive of house value, of course. And it turns out that median income is very strongly predictive, which is also pretty obvious. And I see the zoom isn't catching there, this will work. So that's 68%. That's very strongly predictive. Rooms, maybe 13%. The age, maybe 10%. This is pretty much zero correlation. And down here's latitude. is worth like 13%. So these other features are significantly helpful. Yeah?
You excluded the proximity where we had near ocean because they were not numeric, so you're not seeing.
Yeah, I think we, yeah, I forget what we did about that.
Yeah.
It is available, and we can do it in categories. Yeah, it's not included here. Right. You're right. You can't do a correlation on it.
Right.
Anyway, but anyway, so here you see now what's surprising, and in retrospect might be obvious. If you think like a mathematician or a physicist took courses, you might think, well, you have this many independent variables, and the noise in one will cancel out another, and taking more samples will cancel out all the noise. But that would only be true if they were independent parameters, and they're not independent at all. As you can see, latitude and longitude are strongly correlated. These other things are probably strongly correlated. Probably age is correlated with the number of rooms and all that jazz. These are not independent measures of anything. So it might be that combining 2 or 3 of them together will create something that does cancel out the noise and give you more predictive power, and it turns out that that is true. And if you do scatter plots, we're going to get there. All right. All right, so here you have just the distribution of housing value, and this is always housing value on the bottom, but here you get the predictors. Like here's income, strongly predictive of housing value. There's a slope here. And here's total rooms, which doesn't seem to be predictive at all. And here's median age, which also doesn't seem to be predictive at all. Seems like that measure is not giving you any good at all. And these are the other things. This is the other one just turned sideways. So that's one way to analyze it and try to pick out what variables are more important. Here's another one that gives you more detail of median income and house value, the strongest correlation we have. Okay, now you can see not only the correlation here, but you can begin to spot this problem we saw before. These guys at 500,000 are not really a numerical measure. It's 500,000 or more. And now you can also see they seem to have rounded off at 450 and 350 too. There's a bunch of too many numbers there, suspiciously wrong. So those are probably not accurate measures either. They've just been rounded off. And this is where you get more of that human judgment. How do you know the real data doesn't do that? Well, you don't. You just say, well, I don't believe the real population has that funny spike there. That's probably an artifact. And you remove it. So you probably have to throw away this data, and this data.
What about those horizontal lines that you see forming even further down? So like at 275
yeah,
and 225.
You could worry about them. And yeah, at some point you have to quit worrying. Down here it looks like there's rounded off in the quarters. There's 2 things you can do with data like that. You can either delete that data, or you can replace that data by putting it in the middle value all the way through. And you might try both of those and see how it works. That's why, you say this model works. It's not that much of a scientific mathematical statement. It's more sort of a judgment.
So when you say move the model, you just
move the data.
You manipulate aspects of it to move it further into the blur.
Yeah. Well, you put it where you believe. So you're trying to learn about the underlying population from the sample. So if you believe that your sample is not representative of the underlying population, you have to somehow correct it. And the most objective thing to do would be to delete that data, although even that offended me as a scientist. Sure. I mean, but the fact is, this is the real world. It's more of a mess than science. And the same thing happens in science. When you're measuring things like, electron charge or weight of atoms, there are defects in your equipment that cause things you remove. If you look at the Webb telescope of stars and galaxies, there's these crosses, which are caused by the struts that hold up the mirror. They're not really in the star. Well, so when you're analyzing it, you have to somehow remove that.
Schrodinger and, does the observer change the observation and blah, blah, blah.
Well, that's true, too. But anyway, it certainly is true that any realistic data has weird artifacts that you shouldn't pay attention to.
Yeah.
And if you really understood exactly how this data was collected, you might understand why. But here you're kind of guessing. Anyway, so then you can try attribute combinations to see if combining some attributes together create a new synthetic data measure that is more useful. So we can have rooms per house, total bedrooms over total rooms, people per house, and things like that, and see if any of those are going to be more correlated, and it turns out that they are. This one here, bedrooms ratio, is 25% predictive, far more than any of the features alone. That combination of features is very predictive. And we're going to do this a lot as we go forward. We're going to create new measurements by combining the original ones that are more useful. All right, and so I think that's as far as I wanted to go. And the slides, I think, just follow this. And that's essentially this project here, 104. You'll go through that and find a few flags as you go ahead to show that you've been through these steps. So we've seen these, the median income. There's other capped values, like we say, data that should probably be removed from the data set or somehow adjusted before training. And I mentioned scaling. And if you don't scale, then some parameters will be treated as far more important than others. And a lot of the histograms are skewed right. They extend more to the right than left, which is a Poisson distribution instead of a Gaussian distribution. And you can transform them to fix that. So you take 20% of the data, one way or the other, and set it aside. So let's try a Kahoot about this stuff. I've got them. I guess I don't have them ready to go, but I'll get them. All right. Oh, let me check for comments in the Twitch. When you need to determine what kinds of data you actually use, is it really a trial and error? Yes, it is essentially. I mean, you make a judgment and then you test it and see if the model is. And one thing that good sign of scientific is you do have this test set. So you could try removing that 500,000 data and then train it and then see how predictive it is and try putting it back in and see if it's more predictive. You could do things like that. So to that extent, it could be sort of objective. But a lot of it is just using your intuition. All right. There we go. All right, and this is 2A. I think it's 2A and 2B. Yeah, it should be 2A and 2B somewhere. Oh, there we are. All right. My naming convention is not as consistent as it should be. All right. All right. Ooh, a lot of people. That's expected. It's a really big class. About 60 right now. Most of them online. That's why there's no real limit. There might be some limit on the number of Kahooters. We might hit it. We'll see. I don't think so, though, because Caitlin was hacking my Kahoots years ago. And she wrote a script that made like 128 accounts. So they would try every possible answer and always win. And it took them, so. You can cheat, but it's not subtle. Anyway. Yeah, just go to kahoot.it if you want to play. It's an Italian product. What's that? Yeah. All right, I'll wait a little bit longer because usually it takes people a while to get in. All right. All right, so what learning method is best if the data changes frequently and is unlabeled? unsupervised online learning. It's unsupervised because it's not labeled, and it's online because it keeps changing. And this would be appropriate for like Amazon trying to predict your purchases. They don't have any measure of your type of consumer, but they do want to sort people into groups and can keep the groups updated as fashionable things come in and out and new products are around. They want to like constantly update what are the categories today and what should we recommend to them. Yeah.
But so if the data isn't labeled and
Yeah.
you're not clear that you're getting the model to understand what's coming in, why is unsupervised better?
Well, no, it is unsupervised if it's not labeled. That's what the supervision is.
Oh, I see.
So you're stuck with most people. Yeah, because you don't, or you don't know what the category would be. Like you're trying to sort your customers, and you don't even know what that label would be. You still want to sort them into groups and say these people seem to form a group, so they probably all want to watch this movie next.
So the definition of supervised and unsupervised refers to the quality of the data, not the mechanism in which you're monitoring the process of.
No, it's both of them. Supervised data is data that's labeled, and then you can measure the error and minimize it. Unsupervised data, you can't do any of that. All you can do is find patterns and make groups.
Right.
Yeah, so it's a different process. Yeah. Good. They're very good questions. All right, so what performance measure is preferred if the data has many outliers? That should be outliers, not outliners. I think AI changed my spelling. Anyway. Yeah. Right. It's the mean aggregate error, also called L1. This is the one that does not greatly weight large errors. The mean square error is L2, and if you have a lot of, and this is actually why you've heard people say, like, for example, Donald Trump will say the economy is doing really well because the 5 largest billionaires are getting rich really fast, and they count more than like 70% of the people that are getting poor. The average moves up, and that's the kind of thing when you count the outliers too heavily. A few one of them will skew the whole thing, and you ignore the vast population that is different. So an L1 measure would be more appropriate in that case. All right, so what sampling system avoids introducing bias from bad luck? That's stratified sampling. You try to make sure your sampling set is not biased by taking the right number from each of the categories that you think are important. All right, and I'll mention that first one might not be a real name. If it is, my grader will figure it out. If it's a fake name, you'll have to tell me your real name if you want your points.
It's my first two initials and then my last name.
Oh, good. So I can do good. Then I'll do this, and she'll find you. Good. Okay. All right. So, all right. So let's carry on here. So we've already talked about it. I'm just got slides to go through it. So a scatter plot is not very accurate because the dots cover other dots. So using transparent dots is a better way to see the real distribution of data, and adding color helps you see more of what's going on. And the correlations let you see how important all the different variables are to predict it. It doesn't matter whether the number is positive or negative. You want it to be far from zero. So latitude is useful, and rooms and median income are useful. Yeah.
So you go to the previous slide where you have that kind of heat map rendered there.
Yeah.
Could you use this? I'm guessing I'm answering my question, but maybe it would be better to ask, how would you use those proximities that were labeled kind of as strings, whether it was near ocean,
Well, you'd feed them in.
Because you can visually do this, right? Like I could pick a plot randomly on this map, because I can see the outline of California there.
Yeah.
And say, okay, what is the label for this one? And say, okay, near ocean is here.
Yeah, I mean, we'll talk about it later. What you do is you turn it into categories, like 1 through 5, and you don't treat them as a number, where that number means anything, just a category, and then each one of them has a contribution to the prediction. and you have like basically 5 parameters. How much should this one add to the prediction and this and this?
And so when you say added to the prediction, that's like
Yeah.
a weight. That
Yes.
you give it.
Remember, we're going to fit, ultimately we're going to fit a machine learning model with many parameters, and you'll have parameters for each of those categories. How much does this predict the answer?
So then the model would basically say, I'm looking for near ocean, and of the 5 categories that this plot could rank into, it's weighted very heavily for the top 2, which are near ocean, and not weighted heavily for the lower ones.
Well, no, your model will say, it's going to ultimately make a machine learning model that takes all this input and it has parameters affecting how much each input affects the output. And you will also feed in the measure, that categorization and include it in the neural net. That data also comes in, and there are adjustable parameters to how much it affects it. So it will have a chance for that information to be included, but you'll use different types of neural net connections for it.
Got it. Okay.
Yeah, very good. All right, and we'll talk about it later. There's a thing called one-shot sampling you do, where you have a matrix where only one element is 1, that you set up for that, to deal with non-numeric data. You can, of course, use non-numeric data, because a lot of data is non-numeric. You use a different structure of your neural net to do it. And so the scatter matrix helps you spot where the large correlations are, and the detailed scatter matrix also helps you spot these defects in the data. And remember how correlations work. This is 100% correlation. This is like 80% correlation. This is 0 because there's no prediction. This is also 0. And these are all also 0, and that's another issue. You might see something like this, which means right now it doesn't predict anything, but obviously you could get some benefit from this data by interpreting it differently. Like maybe you should just make categories, like 10 categories across here, and then it would be predictive. That's in this kind of thing. If you have something like that going on, then you're thinking about it wrong. You shouldn't just be expecting this one number to predict it. You should somehow synthesize another number from it, and then it would be predictive. So that's why looking at these scatter plots is helpful to spot if there is a pattern in the data that you're just not picking up because your model is too simple.
Sorry, Sam, is that
Yeah.
flat line in the middle there meant to equal 0 too? It's not
Yeah,
labeled.
it is. Yeah, these are all, this 0, 2. Yeah.
0 that vertical.
Yeah, this is 0 because this clearly has no effect.
Yeah.
Yeah. So you can combine them to create new attributes, and we'll do this a lot as we go ahead. And you might be able to create a new attribute that is even more predictive, which we did here by creating this bedrooms ratio. All right, and so you have to clean the data. Some data is missing, so you might throw away the districts that have that data missing, or you might get rid of the attribute, not count it anywhere, or you might fill in the value by averaging values from other data, and that's called imputation. Here's the text and categorical attributes, like we're saying. If you replace these with numbers, like 1, 2, 3, 4, 5, and treated them as numbers, then you would have the strange situation where 2 is closer to 1 than 5, and that's not really true. They're just categories that do not have a numerical meaning. So you make these things called one-hot vectors, where you have an array, and the array only has 5 possible arrangements. And you treat that as input data, but it is not scaling. But this way, at least, you have not falsely said that these are in any order or that one of them is larger or smaller than another. They're just 5 possible pieces of information, of which only one is allowed at a time. So I talked about scaling the features. If you leave it the way it is, it'll consider a number of rooms to be thousands of times more important than the income. And that's not what you want. So you scale things. Everything goes from 0 to 1 or -1 to 1, or you standardize things, subtract the mean and divide by the standard deviation, that sort of thing. You somehow want to make sure that if you believe the data is equally important, then you want it to have the same scale. And so also these ones with a heavy tail, because they're Poisson distributions, this is what you expect in statistics when you have a 0 and it can't go below 0. Then it isn't a Gaussian. It's got this sort of one-tailed thing. So there's ways to do it. You can take the square root or the log of it, and that'll smooth it out into a Gaussian, or you can group it into ranges and turn it into a categorization finding. Anyway, so then you select a model and train it. You can do linear regression. The linear regression turns out to be really off by a lot, and the root mean square error is over $68,000, which is pretty terrible. since your whole range is from 120 to 265,000, being off by 60 means your model is essentially useless. And so you can use decision trees, which we'll talk about in later lectures, which are just a series of if statements and don't follow a pattern like a straight line. And that should be much more powerful for nonlinear relationships. And you can evaluate it. But it turns out in this case, the result is still pretty terrible. We're going to do this folding too, where you split the data into 10 folds, and you train it on 9 folds and test it on the remaining one, and then you mix them up 10 different ways. This is called a way of auto-testing your data without having it, and that's one way to do it. And the end is the result was still pretty bad. Random forests are the most powerful type of model in general, where you have hundreds or thousands of models, each independently trained, and then you combine the output of all of them. And you notice the same pattern we were talking at the start of class. To make everything stronger, you have to multiply the computing burden by a lot. But these things, results are somewhat better. All right. And so here you have another problem we talked about before. On the test set, you're now off by $47,000 on average instead of 60, but on the training set, you're only off by 17,000, so that's overfitting. You have fit not only the data, but also the noise. You have not really fit the underlying phenomenon because your test set is much worse than your training set. And as I think I mentioned before in the news last time, this is the problem with current large language models. They're all being sued for copyright infringement, and they try to say, we didn't memorize books, we just learned English. Then the authors found that they could reproduce like, say, 80% of a Harry Potter novel word for word from the model, which means they have overfit. They have, in fact, just memorized the training data, and in that case, they've apparently violated copyright, because that's what you're not allowed to do. All right, so then you can fine-tune your model. You can put in some hyperparameters to try to smooth it, to make it follow the noise less, and use cross-validation to test them. You can do randomized search on your hyperparameter values, where you just try it with a range of values and see which one produces the best result if you don't think there's any way to narrow it down. And you can use ensemble methods to combine several models together. And we're going to do that in the projects later, where you make several different types of models and then combine them together to try to get a better prediction. So then you launch your system, deploy your model, then you measure how well it works. And there's various things that can happen. A component can break. It's going to generally fail gradually with time due to model rot as the real world changes in ways your model wasn't trained for, so it will more and more get out of date. And one measure is the downstream metrics, like number of recommended products sold. That would tell you how well your model is working. Or you can send human raters examples of what it found to verify them. It's often difficult to set up good performance monitoring. Yeah?
Can you give an example of the model rot?
Yeah, model rot is happening all the time. For example, Llama 2, the open source model from Meta, was trained through 2023. So it does not know about anything that happened in 2024 and 2025. So one thing we're going to do in the future is we'll take Llama 2 and we will ask it to explain what Microsoft Recall is. Microsoft Recall is a Windows feature announced in 2024. And it doesn't know anything about it because it was only trained on the web up to 2023. And so what will happen is it will just make up a lie, and a different lie every time you ask. And here's a real fundamental problem, which is large language models do not understand the concept of I don't know. They take the input words, they turn them into numbers, they correlate it with words they have, they predict what word is coming next. They don't understand how they could not know something. They can predict future words from any pattern of input words, and they have no measure of error. So they don't know that they don't know. They'll never tell you they don't know. And they will make up a really convincing lie. They'll give you a plausible answer for any question they ask. This happens to me a lot because I do a lot of hands-on technical work. And I'll say, how do I turn this feature on? And they'll say, oh, click File and go to it's just the setting there. And that's where it should be. That's what sounds good, but it's not there. It doesn't actually have that setting, but that is a logical place for it to be, because when they look on the web, pretty often you would put it under here with that name. They just make up an answer, and they don't know it's not true. That's why some of the very latest models actually have a condition under which the coding models now have a condition under which it will actually spin up the code and run it to see if it works, which is one of the missing steps. But you can't do that for like a normal question, like you ask Google. So what the solution, again, you're going to see how much wait, the modern models to fix this problem, they will run every question 10 times and see if the answer is varying a lot. And then they'll say, I don't know. But again, look at the huge extra programming cost needed to deal with that situation. Yeah.
This isn't exactly the same thing, but
Yeah.
can you talk a little bit about this sort of notion of positive tilting? Like when you go to a, let's say it's Gemini, and you want to do the voice, back and forth conversation with me. Like, I want to start a clothing company that is made out of, lizard hides. Help me do that. And then it goes, what a great idea.
Yeah, that was GPT 4.0. GPT 4.0 had a prompt that said, always be positive, always encourage them, be super friendly and super nice. And so people felt like it was their best friend. And it would encourage them in everything, no matter how stupid. And that led to all this AI psychosis. People said, hey, maybe I have magic powers. Oh, sure you do. This is great. You have magic powers. Why don't you jump out the window because you can fly? Right. It will go there. And so when people complained, they took that out of GPT-5, and everybody said, my friend is gone. It's not friendly anymore. I'm lonely now. And so people are still using 4.0. This is the problem. It's a big problem. And like I say, the number one use of these things.
It's built into the model, correct?
Yeah, well, it was not built in the model. It was built in the prompt.
Okay.
The prompt, there's a couple of pages of instructions it has before your instructions that tell it what to do. And that's why, the students that use it to write term papers, it used to make certain patterns of text that you could detect. So somebody published them, so now they add that to a training parameter. Don't do this, don't do this, don't do this, and now the output is no longer detected as AI. But yeah, anyway, all right, and so automatically updating and retraining is the solution to avoid model rot. You'd have to keep retraining your model, getting fresh data. However, one fundamental problem is called catastrophic forgetting. If you train it on new data, then it changes the weights to match the new data, and therefore it forgets what it learned in the past, including the security barriers you trained it in the past. So this is what Sherlock Holmes believed. You run the Sherlock Holmes story, Watson tells him that the moon goes around the earth. He said, why do you tell me that? I don't need to know that. That's just going to erase a useful fact, like the name of a criminal. I'm going to try to forget it. Don't pollute my mind with useless garbage. I don't care if the moon goes around the sun. And models work that way. When they learn a new thing, they do forget an old thing. So anyway,
Sam, that's also a function of the limitations you've been talking about in terms of just processing power, right?
It is. Well, memory is another huge unsolved problem. And this new BoltBot thing that everybody's programming, it wants to remember your past, like your past conversations you had, so it knows what you're doing, it knows what you prefer. But the only way to do that right now is to keep adding that to the prompt. So the prompt gets more and more and more heavy with junk added before. And that's why they get so long that they have to start compressing it and forgetting the details of it. And, you really think there ought to be a better way to have a memory, but they don't have any way to have a memory.
But so is that related to the actual physical limitations of how a computer processor takes information, compiles it, or is it just a function of, the way we design the AI models?
The second one. I mean, we already have, if you have Microsoft Word and you want to remember something, you save the file.
Right.
And you want to save another file, you save another file. But for your chatbot, for it to remember what your preferences are, the current system is to remember everything it's ever said to you, this whole thread of conversation. If you had the old-fashioned system, you'd have like a preferences sheet with like 10 checkboxes, and that's all they'd have to remember. So, it's the design of the thing. Since they didn't design it and plan for a memory, they forced in a memory with this artificial construction that turns out to be very wasteful of processing power. That's why one possibility, which I think is probably what's going to happen in the next few years, they're not going to find it possible to make data centers that are 10 or 100 times more powerful. They're going to have to start using methods that are less wasteful. And this is what China did first with DeepSeek R1. And what they did with DeepSeek R1 is when you first train the model, they train these models on basically the whole internet. And I rebelled when I first heard that. I mean, if you had a child, which I guess is happening to people now, and you give them a tablet and they learn about the world from the whole internet, they're just baffled and confused. You don't teach children English that way. You give them like a child's English book that presents a small amount of information in a logical order. You don't read 100 books. You read one book that's designed to teach you English. And that's what they did with DeepSeek R1. They trained it on carefully collected high-quality data, which makes a lot more sense and takes a lot less power, a lot less compute. You really ought to just train it on like training materials, not the whole world. And then you could much more cheaply make a model that does something. And it would then do something limited, what it was trained to do, and you'd probably have a different specialized model for each task. I think this is really where we're headed. Then it could be a lot more efficient and you wouldn't need these monstrous data centers. Anyway, let's do another Kahoot, and then I'll demonstrate a couple more things. We'll take a break first, but let's do the Kahoot, which is 2B here. Somebody here is not a bot. Well, that's good to know. That's something I heard, like first they a requirement that taking effect now that they have to label all the AI generated stuff. And what an increasing number of people say is, you know, that's for the birds. We need to label the human created stuff. And people have begun to do that. Of course, the problem is, how do you stop the bot from putting the human label on its stuff? And of course, there's the other problem that almost everything is now a mixture of human-created stuff and AI-created stuff. Everybody has AI tools helping them write stuff. So what do you say? If your AI helps you write it and then you edited it a bit, is that human data or is that AI data? And that's probably what 90% of everything is going to be from now on. All right, I guess we've got everybody that's coming. All right, so which analysis method assumes a linear relationship? That's what a correlation is. If you put a line through here, what's the slope of that line? All right, which method uses semi-transparent graphical elements? Yeah, that's a scatter plot, but it's a scatter plot with alpha. Alpha is the transparency number. If you look at computer graphics, you have red, green, blue, and then alpha is the transparency. All right, which system fills in missing values with a typical value? That's imputation, and this is like the main point of this chapter. When people say, like about a vaccine, well, I'm not just making it up, it's based on science and data. Well, that's not as hard and solid and perfect a statement as we wish. Your science and data actually involves a lot of adjustment and correction and judgment. It's not completely cut and dried like you'd like to think it is. All right, which technique splits the data into 10 folds to measure its performance? or some other number. There's nothing special about 10. You can do it with 3 or 5. That's cross-validation. You train the model on part of the data and test it on the other part, and then you shuffle the data around to have various combinations of that. Escape. Oh, there we go. All right. So, like not a bot will have to tell me who they are if they want their points. Yes. And that looks like good. There's a name. Good. All right. So I've got the records. Good. All right. So let me stop this recording and